Now we're going to see the hyperboloid of one sheet. One. The equation is x squared divided by a squared plus y squared divided by b squared minus c squared divided by c squared equals 1. Alright, so this is a hyperboloid. That means that if we do cross section, we are going to have hyperbolas. Yes, we have hyperbolas and ellipses that depend on which plane or through which plane we are doing the cross section. If we do cross section in horizontal cross section, that is in the C plane, in the C equals 0 plane, let's say, that is in the xy plane. So this is 0 and we have x squared divided by a squared plus y squared divided by b squared equals 1. So we have ellipses. If you do horizontal cross section, you will see a ellipse, and is this ellipse that you see here, this ellipse in which the a is the distance from the center, yes, to one of the boundaries of the ellipse, to one of the semi-axes, but that semi-axis is crossing exactly another hyperbola, or it's crossing one hyperbola. Here is crossing the blue, or is touching the blue hyperbola that is made when we do another cross section, but lies in the xc plane. The B is this ellipse that goes from the center to the end of the ellipse, but the end of the ellipse is when the ellipse is touching this hyperbola, this green hyperbola that lives in the CY plane. If you don't want to do it in the XY plane but in another horizontal, so you have x squared divided by a squared plus y squared divided by b squared equals, you could say, c naught squared divided by c squared, and because c naught is just a number, because we are putting c equals c naught, then you have again just a ellipse. Alright, next, and as you see, this is the same ellipse that you have in a ellipsoid, in one of the sections of the ellipsoid, or well, actually in whatever section could be. You know what we're talking about. Next, if you do vertical sections, the vertical section in this case is in C. That is, if you do this section or this section is in the CX plane. So in the CX plane, the same that say when y is equal to 0, or in the plane y equals 0. So you have x squared divided by a squared minus c squared divided by c squared equals 1. You have a hyperbola, and this is this blue hyperbola that lives in the CX plane. If you cut through the x equals 0 plane, in this plane, in the plane y, c, you have y squared divided by square b minus square c divided by square c equals 1. So you have again another hyperbolas that are the green ones. Alright, so we have through cross-sectional cuts that are in the plane that is perpendicular to the, let's say, to the axis in which the hyperbola is, you could say, opening. If it is perpendicular, you have ellipses, and if it is in planes that contain that axis, would be the xc plane or the yc plane, you have hyperbolas. If you have A and B the same, you have a hyperboloid of revolution, and the distance here, instead of having a maybe a ellipse, maybe you could see a cycle, but anyway, the cross sections that are when C equals C naught, these are ellipses centered as the C axis, and the vertex are in the hyperbolas. The vertex are in one of the hyperbolas. Could be in the green ones or in the blue ones. Well, actually, it's I. And next, here I drew them like that in order to see each hyperbole, but here is the surface as you see it. It will be of color. So this is the hyperboloid of one sheet. It is of one sheet because it's yes, it's made of hyperbolas, but it's continuous. You do not separate the pen in order to draw this picture as you do in hyperbolas. So this is called a hyperboloid of one sheet. In the hyperboloid of two sheets, we will review it in the next video, but it's with two minus sign. Here we just have a minus sign, so the numbers or the number of terms that contains the negative sign implies the number of sheets the hyperboloid has. This is just a hyperboloid of one sheet because you only have one minus sign. The other is if you want, instead of doing a hyperboloid like this, if you want a hyperboloid, let's say in the y direction, you will put here minus and here plus. The hyperboloid, that is this, is asymptotic to the elliptic cone. We will touch this also later in the videos, but it's asymptotic to the elliptic cone. This is the elliptic cone. The same way as the hyperbolas in the xy plane, x squared divided by a squared minus y squared divided by square b equals 1, as this approaches or is asymptotic to the lines x squared divided by a minus y squared divided by square b equals 0. That is, if you put 0 here, you have here like this, in order to do it easy. If you put 0 here instead of 1, you have x squared divided by square a plus square y divided by b squared equals c squared divided by c squared. So you have ellipses. So the asymptotic of these ellipsoids are, of these hyperboloids, are this conic ellipsoid, and if you have in the xy plane this, that is the equation of the hyperbola, if you do this asymptotic, or well, this is asymptotic to the lines x squared divided by a squared minus y squared divided by b squared, that is, again, if you put a 0 here, that's the if you put a 0 here. So the hyperbole, this hyperboloid and the ones I'm going to see in the next video are asymptotic to the conic, to the elliptic conic, the same way as the hyperbolas in the xy plane are asymptotic to the lines x squared divided by square a minus square y divided by square b equals 0. And as you can see, there is symmetry in the three axes, in the three of the coordinate axes.